All right, so 12.2a, we have another word here. Now, when this word is being used as a noun, it is pronounced what? Geometric. How do you think it's pronounced when it's used as an adjective? Geometric. I'm just messing with you. It's pronounced the same both ways. Okay. It's not like arithmetic that changes its pronunciation. It's still just geometric. And if you remember when we did our patterns problem, or our patterns project, when we were hanging up the patterns on the boards, on the geometric board, it actually said underneath that, it said exponential. So when you're thinking of these, and you're going through these, and you're like, gee, this looks familiar. It should look somewhat familiar because it's exponential, and we've dealt with exponential before. So, we have a new explicit formula. Dun, 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 dun. And hopefully you recognize some of these terms. Need a new highlighter. So, we need to identify f of 1. What does f of 1 mean? The first term. Okay. And this time we need to identify something called r. There is not a common difference in geometric sequences. There is a common ratio. Now, thinking back to, I think it was mod 14, when we had a test, I gave you some questions where I would give you an XY chart like this, and I would give you various X and Y values, and you would sit there and go, okay, this is plus 3, plus 5, plus 7, remember that? And if those were all the same, it was linear. And then you would go here. And if there was quadratic. And if neither of those were the same, then what did you have to do to show it was exponential? Do you remember? You had to set fractions up. One of the y values divided by the y value in front of it. That's what we have to do to determine if a sequence is geometric. These are y values in an xy chart, aren't they? Yeah? So I have to set up fractions. Now, do not set a fraction up with the first term over the second term. It always has to go backwards. Okay? So 6 over 2 would be my first fraction. And my next fraction would be 18 over 6. Now this is they only give me a couple values here. I kind of wish we had 3 or 4 or 4 or 5 values, just because it's nicer to have more to show that the pattern does indeed continue. So what is 6 over 2 reduced to? 3. What is 18 over 6 reduced to? 3. So guess what? My R value is 3, and yes, this is geometric. Now, when we were talking about arithmetic ones, remember arithmetic was they were either adding the same number each time or they were subtracting the same number each time. Geometric, they are either multiplying or dividing. Now, we don't like to talk in terms of dividing though. We like to stick with terms of multiplying. So if you see something where it is dividing by 2, your brain needs to think not dividing by 2, but multiplying by what? 1/2. Because dividing is really multiplying by the reciprocal. All right? And this, setting up these fractions will help you recognize that. So, I identified that it's geometric. Yes. I identified my R value. What's the other thing I need to do? Write the next two terms. Well, my next two terms, if my R value is 3, I'm going to squish this in here. All I have to do is take the last term I'm given, which is 18, and multiply it by that R value. So I get 54, and then multiply by the R value again, and I get 162. So those would be my next two terms. So? Okay. So if I look at this one, excuse me, if I want to determine that it is a geometric sequence, what am I going to set up as fractions? My first fraction would be 125 over 625. The next one would be 25 over 125, and then the next one would be 5 over 25. Please set up as many fractions as you can based on however many terms they give you. Because you want to see this consistency. That's your proof. So, 5 over 25, I know that reduces to 1/5. What about 25 over 125? 1/5. And 125 over 625? Amazingly enough, 1/5. So, is this geometric? What is my R value? 1/5. So, in other words, 625 times 1/5 is 125. 125 times 1/5 is 25. 25 times 1/5 is 5. And then I'm supposed to continue with the next two terms. What is 5 times 1/5? Well, if I don't know, 5 times 1/5, use that fraction button. It's 1. And then what would 1 times 1/5 be? 1/5. Now, is it okay for me to put 0.2? No. The reason is, if they do not specify fractions or decimals, you always need to stick with fractions. It's just kind of a rule of thumb. The only time it's okay to use decimals would be in a problem like this where they give you decimals to begin with. If they don't give you decimals to begin with, assume that decimals are no good. They're no bueno for the problem. Okay? All right, so let's look at this guy. A little bit harder to find the common ratio, is it? I can't just see, oh, it's multiplying by this very easily, can you? So this is especially where it's important to set up your fractions. What would my first fraction be? 2.31 over 2.1. What would my next one be? 2.541 over what? 2.31. Now, these are just going to be straight division because we're dealing with decimals. So 2.31 divided by 2.1 is 1.1. And let's check the other one. 2.541 divided by 2.31 is 1.1. So, we have something that's geometric. The first part says find the common ratio. Well, common ratio is what? 1.1. Next step says write the explicit formula. The explicit formula for geometric is easier to write than the explicit formula for arithmetic. Remember, arithmetic, you would fill in your f of 1 and you would fill in your d value and then you'd have to distribute and combine like terms. We don't have to distribute and combine like terms. If I look at my formula, I'd have the first term. So I'm going to say f of n is equal to, what is the first term here? 2.1. And then it has a time sign. I like putting my r value in parentheses. So I'm going to put parentheses. And then my r value is 1.1. Make your exponent n minus 1, and you are done. There's no simplifying there. Now, I will get people, there's part 1, I will get people that will want to multiply 2.1 times 1.1. Can I do that? No. Do you know why I cannot do that? Because think about PEMDAS. P-E-M-D-A-S. I have something that has a exponent, an e. If I cannot solve that exponent, I cannot continue with the rest of MDOS. Okay? I just have to stop right there. Sometimes it's easier to think of if you had whole numbers. For example, if I had 3 times 2 to the n minus 1. Is that the same as 6 to the n minus 1? No, because the 3 has nothing to do with that exponent. Only the 2 does, right? But if I multiply those bases, I'm saying the 3 has something to do with the exponent when it doesn't. Okay? So you cannot multiply those two things because one of them doesn't deal with the exponent. So, what's the last part of this problem? Find f of 7, or in other words, the 7th term. So, I can use my explicit formula, 2.1 times 1.1 to the 7 minus 1. Yeah? So f of 7 is equal to 2.1 times 1.1 to the 6th, because 7 minus 1 is 6. And here you go. You're going to be doing the exponent first, which is why you can't multiply by the 2.1 first. So 1.1 to the 6th is that, times 2.1. And let's see, f of 7. Did they round off any of their decimals? They just let it keep going and growing and growing, didn't they? So I'm going to go ahead and leave 3.7202781. I'm just going to leave it like that. So. Now you'll notice with these geometric sequences, and when we get to geometric series, that if you remember with exponentials, the numbers get really big really fast, or they get really small really fast. So you're not going to see me asking for the 47th term of a geometric sequence, because the 47th term might be like 5 billion, okay? It might be something absurd like that. I'm more likely going to be asking for maybe a max of the 10th term, but more likely like the 6th or 8th term, somewhere in there, because those are more reasonable numbers to deal with. Make sense? Okay. All right, moving on to this one. Find the common ratio first, then the explicit formula, and then the 10th term. So, how do I find the ratio? I take a term and I divide it by the term in front of it. So in other words, 4/3 divided by 2. Now that's hideous. I just put a fraction in another fraction. Kind of makes you want to throw up a little bit, doesn't it? Let's have our calculator do the hard work, though. Let me keep going. 8/9 divided by what? 4/3. And what would the other one be? 16/27 divided by 8/9. You ready to see what these reduce to? On my calculator, use your calculator. 4 fraction button 3, there's 4/3. Divided by 2 is what? 2/3. 8/9 divided by 4/3. Again, notice I used the fraction button for the fractions, but I did use the divided by symbol in the middle. 2/3 again. That's looking promising. And then finally 16/27 divided by 8/9, 2/3. Okay. By the way, if for some reason I didn't have a calculator, not saying that's going to happen, but if I didn't have a calculator, how do you do 8/9 divided by 4/3? Wouldn't that be the same as 8/9 divided by 4/3 written this way? In which case you would do 8/9 times the reciprocal and go from there. Does that make sense? I'm just using my calculator to do that for me to save me the work. Okay? All right, so what is my common ratio? 2/3. My explicit formula, f of n equals the first term times the ratio to the n minus 1. So what's the first term? 2. Parentheses, the common ratio is 2/3 to the n minus 1. That's my explicit formula. What's the last thing they ask me? The 10th term. So f of 10 is equal to 2 times 2/3 to the 10 minus 1. Or in other words, f of 10 is equal to 2 times 2/3 to the 9th. Plug that into your calculator and let me know what happens. What's happening? It's too freaking ugly of a fraction. My calculator does not like doing, I'll do parentheses, 2/3 to the 9th power. I forgot the 9. But 2/3 to the 9th power, it goes straight to decimal. And even if I use my fraction to decimal button, my calculator is saying, nope, too ugly. Not going to do it. So, how do I stick with that whole, it's giving me fractions, I need an answer in fraction form, when my calculator is protesting? Here's how I'm going to do it. I'm going to keep the 2 out in front. In here, I'm going to call this 2 to the 9th over 3 to the 9th. You okay with that? Just distributing that exponent. So far, so good? Good answer. What is 2 to the 9th power? I think I can do that on my calculator. 2 to the 9th is 512. What about 3 to the 9th? Yep, 19683. So I can get those numbers individually, it just doesn't like it as a fraction. Now, how do I multiply that by 2? It's really multiplying by 2 over 1, isn't it? So, on the top, I have 2 times 512. What's 2 times 512? 1024. And on the bottom, I have 1 times 19683 is 19683. And we're just going to assume that we're reduced there at that point. Because if I were to try to plug that into my calculator, oops, over 19683, it doesn't want to reduce it for me. It just wants to go to decimal. This is even, that's odd. I'm assuming it's reduced as far as it can go there. Okay? So that's how you kind of get around the whole, if it happens to be a number that's too big for your calculator to deal with. Okay? All right, next problemo. Given f of 5 is equal to 54 and r equals 3, find the explicit formula. Thinking back to the explicit formula, what are the two pieces of information I need? I need the first term and the ratio. Well, they've given me half of that. They've given me the common ratio is 3. They have not given me the first term, though. So at this point, I know that f of n is equal to whatever f of 1 is, we don't know yet, times my r value to the n minus 1. That's what I know at this point. Yeah? How am I going to use the other piece of information to help me? Well, they're saying when I plug in n value of 5 in other words, when I make this a 5, and I have my r value, and I have my f of 1, what is the answer that I get? 54. If I can plug that in, I can now solve and figure out what f of 1 is. You see what I did there? So the 5 is what goes in for n, and 54 would be your f of n. So let's see. 54 is equal to f of 1 times 3 to the 4th. What is 3 to the 4th? 3 to the 4th is...
64.
No. 81. If I divide by 81, f of 1 is equal to 54 over 81 2/3. So I now know what f of 1 is. Do I know what r is? So my formula, my explicit formula would be f of n is equal to 2/3 times 3 to the n minus 1. I know it's hard to see there. N minus 1. Not too bad? Pretty much the same thing you had to do with the arithmetic ones, right? Yeah? All right, ready for the back page? Oh my gosh, there's 2 pages. Back page goes fast, don't worry. Okay, on your homework, you are going to have a couple problems where you're going to have to graph. Now, the graphing is not hard, I promise. In the assignment, sometimes they're going to give you maybe 3 or 4 terms, but they're going to ask you to graph 6 terms. So in other words, if they only give you 4 terms, but they ask you to graph 6 terms, You have to look at the pattern to figure out what the next terms are until you have 6 terms to graph. Does that make sense? So if I look at this one, the first term is 800. The second term is 400. The third term is 200. The fourth term is 100. And the fifth term is 50, but I need to graph 6 terms. So I need to sit here and look, what are they doing each time, and what is the 6th term going to be? Can you figure it out? They're cutting it in half each time, right? So this one is going to be 25. So I have to fill in that one. Now, on my graph, my x-axis, which is called my n-axis here simply because that's my title of my x column, I do not need to label. It is going to be assumed that you are counting 1, 2, 3, 4, 5, 6, that each line is 1. Okay? But this side, I need to figure out how am I going to fit all of those in there. Now, yes, I could just count by like 200s and be done with it. But if I count by 200s, my whole graph is going to be like squished right into here. Is that going to be very informative for me? No, so I don't want to count by 200s. If I count by 100s, I'm going to be a little bit bigger, but I think I can count by even 50s. If I do every other line as 100, can I get up to 800? Yes. So if I count every other line as 100, you want to use as much of the graph that's given to you as possible. Okay? That allows you to zoom in basically on the graph to as much of it as you want to see. So let's plot our points then. 1 goes with 800. Again, these are 1, 2, 3, 4, 5, and 6. You don't need to label those though. 2 goes with what? 400. 3 goes with 200. 4 goes with 100. 5 goes with 50. And 6 goes with 25. Do I connect the dots? No, why not? Again, this is discrete. 1.5 here, does that have any meaning? Should 1.5 be able to give me a result? No, because there's no 1.5th term. It doesn't even make sense, right? There's only 1 800, 2 40, 3 200. There's nothing in between those guys. So do not connect your lines. This should look like an exponential graph to you. Yes? Does it? Does it look like exponential growth or exponential decay? Decay. Well, let's think about that for a minute. What is the R value up here? It's not 2. 1/2. So if I think about it, in the formula, it would be 800 times 1/2 to the n minus 1, right? What happened when this value was a fraction? That was the very definition of exponential decay. So these things should be ringing bells as far as stuff we've done before. Okay? Also, there would technically be an asymptote here, right? If I'm dividing by 2 and dividing by 2 and dividing by 2, am I ever going to get to 0? Like, think about it. If you take a piece of paper and you cut it in half, and then you cut that half in half, and then you cut that half of a half in half again, you can keep cutting in half and half and half and half, and technically, you're never going to get to the very end because you can always cut what's left over in half. There's always going to be something left over, even though you're going to be stopped physically by your ability to cut a piece of paper that's that small. So it's kind of a weird thought, but you're never ever going to stop. You're just going to get a smaller and a smaller and a smaller piece of paper. That's why it's got an asymptote there. It's going to get closer and closer to being non-existent, but it's never actually going to disappear. Okay? The reason why we're doing graphing is because some of our geometrics show up like this, and some of them show up a little bit differently, like this next one. What do you notice about this next one? Anything? It's positive and negative. I have my first term is 2, second term is negative 4, third term is positive 8, fourth term is negative 16, fifth term is positive 32, sixth term is negative 64. What would you say is the R value? The R value is negative 2. When your R value is negative, your graph is going to look a little funkier. Okay? Now, if you notice, the x-axis is now right in the middle, or the n-axis is right in the middle. We're still going to be counting by ones on our x-axis, so I don't need to label that. But my y-axis needs to go all the way down to negative 64. And what's the highest it goes to? 32. Now, I think the 64 I'm a little bit more concerned about having room. I'm going to count by 8s. So negative 8, negative 16, negative 24, negative 32, negative, hang on, did I do that right? Yes. 40, negative 48, negative 56, negative 64. I think that's about the best I can do there. And then on the positive side, 8, 16, 24, 32, 40. I can stop there because I only have to get up to 32, right? And let's plot our points. 1, 2 is going to be like right there. 2, negative 4. 3, 8. 4, negative 16. 5, 32. And 6, negative 64. What's going on with that graph? Does it look exponential? It doesn't look exponential, does it? What's happening to it? It's kind of bouncing back and forth, isn't it? It's going from above the x-axis, below, above, below, above, below. Where's my next one going to be? It would be above, even further above than that one, and then even further below. So does it seem like it's approaching an asymptote, or is it just getting bigger and bigger? It's just bouncing and getting bigger and bigger and bigger and bigger. That's going to mean something when we get to our series tomorrow. Okay? Today I just want you to graph some so that you can see that there are some that turn out nice like this. There are some that kind of go crazy like that, and it'll just kind of keep bouncing up and down over and over again. Okay? All right. I think that's it. Any questions? Happy studying.